years ago. And I've been coming here a few times a week, working in Peter Hosman's group as a visiting scientist. I graduated from Rutgers University, and then I went across the river and got a PhD at Columbia University in nuclear chemistry and low-energy nuclear physics. It was like a combined degree between the physics and chemistry department. Then I spent about 15 years at Argonne National Laboratory, and the rest of my career, about 31 years at Lawrence Livermore National Lab, with a couple of sabbaticals in between. I've worked in many different areas: nuclear chemistry, low-energy nuclear reactions, high-energy nuclear reactions at the zero-gradient synchrotron at Argonne, and then I sort of drifted into material science. I decided I didn't want to search for islands of stability for the next 40 years, and I decided to get into another dying field, nuclear energy. And it turns out that that was really actually a good choice. It's very exciting, and there are many unsolved problems in nuclear energy. Personally, I believe that nuclear energy has to be part of any rational portfolio for energy production in any country that wants to have energy security. But that's my opinion. What do I know? I'd like to tell you that I'm really pleased to have an opportunity to tell you about the activities and what I've learned during the last year and a half. I've been working on a problem that has bothered me for about 10 or 15 years, and has bothered the materials nuclear energy community for approximately 50 years. And it still remains to a large degree unsolved. But I'm going to show you that some things have happened, not because of me, but because of other workers, particularly a group in the Ukraine, led by Kalchenko at Kharkov University, that shows the way towards solving a problem, which is how do you do accelerated experiments at the dose rates of heavy ions that are of sufficient quality and accuracy and can be assigned reasonable uncertainties that they can serve as engineering tools. Because if you talk to many nuclear engineers, they'll tell you that they believe what happens with neutrons, but they don't necessarily believe that what happens with ions is relevant to what's happening in a reactor. And I'm going to sort of tell you a different story. And if I'm successful in telling you this story, I hope some of you newbies might actually make this topic a piece or a part of your thesis work. So let's begin. Oh, I have a new toy here, so I have to be sure I know how to work it. Let me see. I think I have to press this button, and then it works. So we're going to talk about the experimental determination of a swelling equation. We don't want to get that confused with another thing I'm going to talk about, which is the swelling curve. And the swelling equation is a four-dimensional animal, and you'll see about what those dimensions are. And what we're really talking about is a single equation for swelling in a particular material from as high as dose rates of 10 to the minus 2 dPAs per second to dose rates as low as 10 to the minus 9 dPAs per second. So that's heavy ions to neutrons. So this is the low end of a thermal reactor, for example, and this is sort of the high end of what you do with heavy ions. And I hope this becomes relevant by the end. I thought it was sort of fun to put in this quotation. One ring to rule them all, a single swelling equation. Okay. History of swelling. This is a quick history of swelling. The first observation of swelling, which was not predicted, by the way, so this is a serendipitous experiment, was 1967, a little over 50 years ago, by Cawthorne and Fulton. This was done in a fast reactor in Great Britain. When this happened, the reaction in the community was complete and utter bedlam because nobody believed that swelling existed. Here's an example of swelling. If you can read these numbers here, you'll see that all types of things are talked about, the material, the temperature, and the dose, but the dose rate is not talked about at all. And of course, that's what we're going to be focusing on, is the role of dose rate in these types of observations. Swelling was responsible for restructuring of the entire U.S. and international fast reactive materials programs. And there were many international and national symposia pulled together, and everybody took out their pencils and their Martian calculators and were going away using rate theory to try to understand what was happening. So there was an intensive research and development effort devoted to fuel cladding and to the duct alloys in the period of around, actually it began in the 1970s, but in the 1980s, and some applied work was still going on as late as the 1990s. I think a lot of this is being renewed now as new materials are being introduced for new reactor generations. And for also for accident-tolerant fuels, for example. But here's an example of a stainless steel swelling in an FFTF fuel pin bundle. You can see that the swelling is quite severe for many of the fuel pins. There's been a continuing level of basic work, although there's a tendency to believe that swelling is understood and that materials do exist and have been discovered that resist swelling. And a good example of this is HT9. Of course, the question then is, what doses are you talking about, what temperatures are you talking about, and what dose rates are you talking about? So is HT9 really resist swelling? And if it does, why does it resist swelling while stainless steels do not? So, is accelerated testing with ion beams alone possible? Well, I wouldn't be standing here if I didn't think the answer was yes. So why bother? I want to tell you what the swelling curve is. I want to give you a quick review of dpa-rate effects. I want to show you the confusion about swelling. Then I'm going to demonstrate the method developed by Kalchenko and his co-workers in the Ukraine for a parametric determination of a swelling equation that covers a wide range of dpa rates. And then I'll show you how that swelling equation is used to bridge the dpa-rate gap, that is, the gap between ion beam experiments and fast reactor and thermal reactor neutron doses. So ion beams to thermal reactor neutrons. Give you one or two examples in Austenitic Steels, and then tell you what I think we've learned and what's needed to go forward. So rate theory says that the same differential equations determine swelling at 10 to the minus 2 dPAs per second as at 10 to the minus 9 dPAs per second. And that is a really ostentatious. This is a Trumpian type of expression, if you will. Okay, so let's go on. Why do we care about being able to predict low dose rate swelling with using high dose rate ion beam swelling? And the answer is that at dpa rates, displacement per atom rates of 10 to the minus 4 to 10 to the minus 2 dPAs per second and temperatures of 500 to 700 degrees C, we can do ion beam swelling experiments in a matter of days, or at most a week. In fast reactors, we're in a different regime, and it takes years, sometimes close to 8 or 9 years, to do certain types of material studies with regards to swelling. And if we move on to a PWR or a BWR and actually try to do material studies at those dose rates, the experiments can take decades for just the irradiations. Of course, all of this also requires a considerable amount of post-irradiation examination, and that always becomes one of the cost-limiting aspects of doing experiments, whatever the dose rates are. So accelerated testing in days allows us to get ahead of the curve. days of ion beam irradiation instead of decades in a reactor. If we really could do this, this is a discontinuous change in the methodology for developing new materials, or actually understanding the aging of materials that already exist in the current fleet of reactors. So here's how it is that the swelling curve is understood as a consequence of non-equilibrium rate theory. I'll try to go through this slowly. On the left, this is the work of Wiedersich. It's actually seminal work that came out of that original discovery of swelling in Great Britain. And this shows up in half a dozen textbooks, I believe. What you see here plotted as a function of inverse temperature is the vacancy concentration, which at high temperatures to the left is the thermal vacancy concentration, this straight line from which you actually get an Arrhenius curve, and you can determine things like the vacancy formation enthalpy. This Nike-like part of the curve here, it represents two different dose rates, 10 to the minus 4 displacements per atom per second and 10 to the minus 6 displacements atoms per second. And the cluster of three curves represents different sink efficiencies for vacancies. And what you end up with in this calculation is the sum of the thermal vacancy concentration, which is getting smaller and smaller and disappearing, and what is called the non-equilibrium or supersaturation concentration of vacancies. You don't get swelling if you don't have vacancies in excess of the thermal amount, so you only see swelling in this regime. Now, what does the swelling curve, not the swelling equation, but the swelling curve look like? And that's shown over here. For the 10 to the minus 6 dPAs per second, and one particular sink efficiency, we have this curve, okay? And just keep an eye on where the temperature is of the peak, okay? And then if I go to higher dPAs per second, in other words, increase it by a factor of 100, then I get the dash curve over here. And what you see immediately is that there's been a significant temperature shift to higher temperatures, the magnitude has dropped, and the width has gotten narrower. And this is exactly what you see if you actually do experiments where you measure the swelling curve. On the top, you see swelling curves for 304 stainless steel irradiated with a carbon-heavy ion, which has been irradiated to 41 dPa, with and without pre-implanted helium to simulate the effect of nickel transmutation products in the 304 stainless steel. And down below, you see a 304 stainless steel where it's been neutron irradiated to a similar number of dPAs. And again, the phenomena that was seen from the rate theory calculations of Wiedersich is represented here. Increased dose rate narrows the curve, lowers the intensity, and shifts the curve to higher temperatures with higher dose rates. So that's the phenomena that we really want to be able to model completely. Now, turns out that about a half a decade later, a series of papers began to be generated by the theory group led by Mansour at Oak Ridge National Laboratory. And one of the important things with regards to swelling is demonstrated here. This equation is a simplified version of a much bigger equation that describes what we expect to happen to the peak in the swelling curve. You remember we just talked about the swelling curve. What happens to the peak in the swelling curve with regards to a shift in temperature when you change the dose rate, G being the dose rate. So the ratio, the log of the ratio of the dose rates enters into this, and this is the shift in the temperature associated with that. So we're tracking what is called in the literature invariant swelling, but it's really not invariant. What we're really doing is we're tracking the peak of the swelling curve with dose rate. And to use this equation, you need to know the vacancy migration energy and the vacancy formation enthalpy, and this little nasty number here called n, which varies between 1 and 2. This is probably, with regards to swelling research, the most misused equation in that area of study. People use this to extrapolate from a single point, something that's pretty hard to do. But you need at least 2 points to actually utilize this equation effectively, because nobody ever really knows what n is. And that can be quite significant when you play with the numerology of this equation. But how does this equation stack up with actual experimental data? And here you see, for example, copper and nickel, and you see the peak in the swelling curve plotted as a function of temperature and dose rate, or dPAs per second. And I think the more interesting of these 2 plots is the one for nickel, because here you have proton irradiations, heavy ion irradiations, electron irradiations, and then down here you have neutron irradiations. So here you see the gap that I was talking about, the gap between high dPA rates and low dPA rates. What's interesting is that to a first approximation, even though this equation is formally mathematically a power law equation, it actually is well described by an exponential. And so we'll just treat it for the purposes of this discussion as an exponential. So what did we learn? Key point: to quantify the effects of dPA rate, you must track the peak in the swelling curve. If you don't track that peak in the swelling curve, you're basically wandering around in the woods without a compass. Although you can always look for where the moss is growing.
I've always understood swelling to be a function of the temperature normalized to the melt temperature. And so why wouldn't you want to consider that for this kind of fit rather than, here we have 2 different elements, and they clearly, are drifted over by T over T melt, but you would think the shift would also be.
Yeah, that's interesting. I actually spent an afternoon going through the literature, not only for this copper and nickel, for Austenitic Steels, to see if I could create a normalized curve based on some type of relationship to the melting point, like the ratio to the melting point or some other crazy functionality. It doesn't work very well. So I don't know the answer. I'm sure the answer lies in a detailed analysis of the underlying rate theory, but I can't give you a smart answer to that. I have tried to make that happen, though. It doesn't work, at least with data that I was able to find. So if we now consider Austenitic Steels, and I plug some reasonable numbers in for the vacancy migration energy, the vacancy formation energy, and I just picked a number for n out of the air, which happens to work, so to speak. You'll see what I mean by work in a moment, of 1.8. Then here are the data points, and there is the exponential plot of the data. A power law plot, of course, would fit it perfectly. You'll get an R-squared coefficient of 0.9999. But as I said, we're going to use a exponential just for the fun of it. If I take some real data out of the literature, in other words, for Austenitic Steels, then here you see ion beam irradiations where the swelling curve has been measured, and here you see neutron irradiations where the swelling curve has been measured, and this is fit nicely with n equal to 1.8. So this says that even for a complicated system, not a pure metal like copper and nickel, this Mansour model that tracks the peak in the swelling curve as a function of dose rate looks like it holds. Okay, confusion about swelling. These are swelling curves that you're looking at here for a 20% cold work 316 stainless steel. And you can see that there is a incubation phase. This is where little embryonic cavities are growing. These cavities eventually begin to reach what's called critical size. The critical size is the point at which vacancies become trapped, but because of the increasing radius of curvature, they can't escape anymore at that particular temperature, whatever it may be. And that happens over a range of doses. Not all embryos reach the critical point at the same dose. And then eventually you get to what is called by engineers breakout, and what physicists and material scientists call steady state. That's the point at which you get a linear increase of swelling. And in fact, there's this rule of thumb promulgated by people like Frank Garner and others that say that for thermal reactors and for austenitic steels, this number is something of the order of 1% per dpa. But you see here, even though the data is sparse, what Frank Garner would say is that eventually this would get to 1% per dpa, but it looks like it hasn't gotten there yet. What you're going to see as we go through the development of the swelling equation is this notion of 1% per dpa is pure garbage. And that, in fact, these guys here are never going to get to 1% per dpa. So what's missing from this complicated set of data? These data are confusing because the dpa rate is the hidden variable. If you knew what the dpa rates, this data would start to make more sense, and the next slide shows an example of that. So here you have an iron chrome nickel alloy, austenitic material, all at the same temperature in a fast reactor, but with a variation in dose rates of about a factor of 20. And although the data is sparse, you can see now what's happening. As the dPAs per second increases, the incubation period appears to be increasing, while the breakout slope seems to be decreasing. Just the type of behavior that was actually predicted by the Vietersig mean field theory, rate theory calculations. So what this says, and what we were saying right from the beginning, is swelling is a function of not only dPAs in temperature, but dPa rate. And you need to know what that rate is.